Hi, my name is Jack Bida, and I'm going to be talking about machine learning applications to knot theory, my master's thesis, supervised by Davide Micheletto. So before we get too far into the question of machine learning and things, I just want to make sure we're all on the same page around the basics of knot theory. So this is a knot, or if you like, really a mathematician's knot. So that's to say it's tied on a loop of string, as opposed to something with loose ends, and that lets you sort of pull it apart without it getting untangled. And mathematicians have been interested in telling apart knots for a long time. So if I give you two different knots, you can ask whether or not it's possible to sort of deform one so that it looks like the other. So people started putting together these knot tables a while ago, and in fact, these two knots were categorized as different knots in the first knot tables a few hundred years ago, and they stood as different knots for about 100 years until people realized that in fact they're the same. You can deform one to the other. And so this highlights the fact that basically telling apart knots is really hard. These guys stood as separate knots for a very, very long time. Now, some people wrote a paper recently where they showed that machine learning networks are really, really good at telling apart different knots. And this is exciting if you're a mathematician, because it means that maybe the machine learning network is learning some kind of topological invariant, some kind of new mathematics that we don't know. And if you're a physicist, it's exciting because physicists need to tell apart kind of knotted structures all the time in things like polymer physics, where you want to know what kind of polymer structure you have. And so there's lots of interest in this. And so basically in this work, we're gonna extend these results, but we're gonna extend them to a wider class of links. So a link is just like a knot, except it has multiple components. So the left guy here is a knot, the right guy here is a link. It has two, in this case, two components. And so we're gonna be studying links. And the general idea is that we're gonna start with a bunch of different links, these guys up at the top, and we're gonna shake them up using some molecular dynamics software called LAMMPS. So basically, if we want to train a neural network to classify the links, we need to have many, many different geometric copies of the links that are all kind of topologically the same. So for example, this guy here with two unlooped rings, we've shaken it up here, you can tell it looks like that one, whereas these guys here, it's harder to tell which one they correspond to. So then we're just going to take all of this, we're going to feed it to a machine learning network, and we're going to see what comes out. And in fact, the key result of the previous paper wasn't that machine learning was really good at telling apart knots directly. It was that when you train the machine learning network not on the coordinates of the knots, you don't tell the computer where the knot is, but you tell the computer what the value for the Writhe density matrix of the knot is, or in this case, the link. And so people are excited because maybe this Writhe density matrix includes some kind of new topological invariant. So what is the Writhe density matrix? The Writhe density matrix is, in the most basic sense, just a function that you can compute on the coordinates of the knot that gives you some kind of topological information. So you choose the magenta component, you have the green component, you choose a point on each of the two components, and you evaluate this function, and that is a point in your matrix. So if we've taken this knot and we've kind of discretized it into a set of 60 points, then we're going to have an index for component 1, an index for component 2. We evaluate at that index, and that's a point in the matrix. And you can compute the Writhe density of component 1 with component 1. You can compute the Writhe density of component 1 with component 2, 2 with 1, 2 with 2, and so on. And so this gives you this 2 by 2 block matrix. You'll notice the matrix is symmetric. That's not a big surprise. That's just because if you look at this function, if you exchange the orange and the blue components, then the function remains the same. And so if you take away only one thing from this slide, it is that the Writhe density matrix is just a function you can compute on the knot that may or may not contain topological properties. All right, so now we're ready to get started. So these are the 6 links that we're going to be studying. They have their fancy name in terms of Alexander Briggs-Rolfson notation, but you can also refer to them in sort of the common parlance as you would at the cocktail party as the unlink, because it's not really a link, the Hopf link after Mr. Hopf, and so on. And so we're going to take these knots and we need to put them into code. So we need to download them from, in this case, a software called Knotplot. We take them, we discretize them into a set of points, and now we have them. Now, if you want to train a machine learning network on pretty much anything, you're going to be better off if all of the inputs are the same size. And so we need to make sure that all of the components of each of the link contain the same number of points. And so to do that, we're just going to take all the components that have fewer points than we'd like, and we're just going to add on a little appendix to extend them. And so when we do this, we get our new set of extended links from notplot. And you can kind of tell just visually by hand that we haven't broken the topology of the links by doing this extension. And now we're ready to generate our training data. So we'll just take these links and we'll shake them up using this molecular dynamics software. And here's an example of the shaken links. But of course, we have 1,000 different copies of each of these links in the training data. And so what comes out of the neural network? So if we just go ahead and we train up our neural network, we're ready to go, we get various results. So there's a lot going on in this slide. The key takeaway is that if you want to measure the success of a classification network in terms of one number, the number you're looking for is the accuracy. So the accuracy is between 0 and 1, or 0% and 100%, and it measures the fraction of the links that were correctly classified by the network. So in this case, a network trained on the XYZ coordinates alone has an accuracy of about 40%. So random guessing would be about 16%. A neural network trained on the Writhe density matrices has an accuracy of about 97%. So that is way, way better. It's very, very good. Now, if we kind of zoom in on this, this is called a confusion matrix. It gives you a breakdown by link type of how the network is doing. So for example, in this case, what we see is that the link that has a true label of the unlink, so it is an unlink, is correctly classified as an unlink by the coordinate trained network 85% of the time, whereas it's 94% of the time correctly classified by the Writhe density matrix trained network. And so, you can look around here and basically confusion matrices make it very clear that the Writhe density matrix trained network is doing quite well and the coordinate trained network is not doing very well. Now, at this point, I just want to point out that when we made an arbitrary choice earlier of extending the links, we extended them to an arbitrary number of points, right? We could have extended them very, very large. We could have extended them a little bit so that we had kind of larger or smaller links. I just want to point out that if we plot the accuracy of both the Writhe trained network and the XYZ trained network as a function of the number of points per component, they're pretty much constant. Now, XYZ varies a little bit, but that's just telling you, XYZ isn't learning anything. It's grasping at straws. Don't worry about XYZ. The key point here is that Writhe is doing very well. Okay, now it shouldn't surprise us that Writhe is doing so well at first, because there are some global features that the machine learning network can learn that aren't really, very important. So if we take that, remember, we're training on that Writhe density matrix. If we were to simply add up all the elements of that Writhe density matrix, so machine learning network can certainly learn how to do that, what we get is this distribution in the training data. So this is to say that in the training data, most of the Solomon links, so that's the green guy, most of the Solomon links have a total link Writhe that's around -3. Most of the unlinks have a total link Writhe that's around 0. And so a machine learning network will easily be able to tell apart these two guys just based on adding up all the numbers in the Writhe density matrix. And this is not a topological invariant. This is just a fluke of the fact that the kinds of configurations that are accessible to lamps, that are likely to be achieved by lamps, have particular values of total link Writhe. Now, similarly, the 1-2 linking number, you can see here, distinguishes the links very well. So the 1-2 linking number is not the sum of all the elements, but the sum of all the elements in the top right block. Now that is a topological invariant. That's why we see these basically Dirac deltas that go off the screen. What they're telling you is that 100% of all of the unlinks in the training data have a 1-2 linking number of 0, as to be expected because the linking number of the unlink is indeed 0. And so it's no surprise that the network is succeeding in distinguishing these guys, because there's plenty of information here. Now, if we test what the network can learn by subtracting off these global features, so we can, instead of training on the whole network, from now on, we're just going to train on the network minus the global features. So subtract off the sum of each of the 4 blocks from the blocks so that we don't have these features to learn. And when indeed you do train the network on these guys, what comes out is we've got a new confusion matrix, and the accuracy is still very, very high. So it's less than 97%, but 94% is still quite good. And so, indeed there is something going on here just beyond the total link Writhe and the 1-2 linking number. All right, so there's a few other kind of arbitrary choices we made that are worth investigating. The first one is we chose a particular value of the temperature of the lamp simulation, and we can see what happens if we tune that dial. So we had a temperature before of 1 in arbitrary simulation units. And you can see as you increase the temperature of the simulation, basically the knot gets more kind of twisted and tangled up, which generally has the effect of increasing Writhe. What happens to the accuracy of the network when we change the temperature? Well, if you change the temperature, the accuracy, it decreases, moderately when trained on the Writhe, but, otherwise stays quite good, right? Still always above or always around 90%. XYZ is terrible the whole time. Of course, you'll notice it shoots up at low temperature. That's just telling you that when the links don't move very far from their initial configurations, then the XYZ is indeed able to categorize them because basically all the elements in the training data are the same. And so, this is a little bit surprising. It's a little bit surprising that the Writhe accuracy remains so high across such a wide temperature range, because if it was learning nothing but global features, we would expect it to go down quite a lot, because basically the width of those distributions, the overlap of the distributions we saw earlier for things like the total link Writhe, increase as you get to higher temperatures. So basically the state space that's explored of values of total link Writhe gets larger and larger. So this plot is just showing you that as you increase the temperature, the interquartile range, so the width of the total link Writhe histograms, increases. Now, there's an interesting outlier that comes up here. If you zoom in on this guy, this is sort of completely unrelated, but actually one of the more interesting things that comes out. This outlier is showing you that the width of the total link Writhe distribution for this particular link shoots up at a particular temperature. And what's going on here is actually that there's a particular configuration of this link that's preferred at low temperature, and it has this distribution of total link Writhe. It's sort of centered around 6.4. Whereas at high temperature, it has this distribution that's preferred because it's in this configuration. And so what's going on at the medium temperature is the width of the distribution shoots up because it goes bimodal. So this is totally unrelated, but a nice little feature that comes out is that you have this kind of two stable states at different temperatures. The last thing that we wanted to try is what happens if you add in Gaussian noise to the training data. How does the network respond? So we're going to add in basically random values sampled from a Gaussian of standard deviation sigma to each of the x and the y and the z coordinates of each of the points in the link. Now, obviously, this is going to destroy the topology. We're not worrying at all about keeping the topology the same. We're just seeing how it deals with small perturbations. So this is kind of a visual demonstration of what happens if you add this noise. You can see by the time you get to sigma is 10, you've lost all kind of meaningful information. But, sigma is 0.1, 0.2, even up to 1, right? You're retaining some of the ideas, though you might be breaking the topology. And what happens to the networks? Well, the accuracy of the Writhe trained networks drops rapidly when you add standard deviation noise above 1. And XYZ, in fact, even wins out. This is really just probably a reflection of the fact that the XYZ is capable of learning the center of mass of each of the components, which is going to be constrained by the geometry and won't be changed by the addition of Gaussian noise on average. But, if you wanted to be generous by looking at this plot, you would say, hey, I notice that when you add noise that changes the topology, so that's to say Gaussian noise, the accuracy of the Writhe trained network does change quite a lot. Whereas when you add noise that doesn't change the topology, i.e. thermal noise, the accuracy of the neural network stays pretty constant. And so clearly, this is an indication that the Writhe density matrix includes some kind of topological invariant that's being learned. Now, I don't think this is really the right way to go, but it is compelling that the Writhe trained network fails when you add topology changing Gaussian noise. So the last kind of case study that I want to talk about is the case of the Whitehead link. So this is the Whitehead link, and it's a special link because it has a mirror image that's not the same as it. So the left-handed Whitehead link and the right-handed Whitehead link are topologically distinct. You can't exchange one for the other. And it's also special because it has a 1-2 linking number of 0, which means that the left and right-handed sides will both have linking number 0. And so a network might have difficulty distinguishing these two links. Now, in fact, first off, a network isn't going to do super well if we train on the full Writhe density matrix, because the total link Writhe of the two chiralities already distinguishes them super well. So it's just the linking number that's going to be the same. And so if we train only on that 1-2 block, that's really where we're going to be able to put the Writhe density matrix through its paces. And surprisingly, if you like, what we see is that the Writhe density matrix train network does really well, even when you train only on the 1-2 linking number block, so only on that top right block. Whereas again, the XYZ is just, it's 50%, completely random. And so, you know, again, this would be really quite compelling, but the Whitehead link case study also introduces a new kind of dangerous point. And that is this plot, which will take a little bit of time to unpack. So this is a series of histograms of the total Writhe of each of the two components. So the total Writhe is the sum of all the elements in the top left block. So that's the Writhe of component green with component green, and the Writhe of component magenta with component magenta, for example. And so, you know, what we have here is this green trace is showing you the total link Writhe of this green component in the training data. And we have the total link Writhe of the magenta component of the training data. And so it's no surprise that both of these plots are mirror image reflections, because basically when you take the mirror image, you're going to expect the mirror image for the total Writhes. However, what we should expect is that these plots are the same. And the reason we should expect that is because actually, topologically speaking, the magenta component and the blue component are the same. It's possible to take the Whitehead link and deform it so that those two components switch places. Similarly, for the magenta component and the green component, it's possible to deform it so that these two guys switch places. And so what this is telling us that LAMMPS has not produced a data set that reflects the underlying topological properties. There's an asymmetry in the data produced by LAMMPS when there is a symmetry in the topology. And so if you like, this is a massive red flag. It's just telling you that you shouldn't be trusting LAMMPS to produce data for your simulation if you are interested in having data that reflects the topology rather than the initial condition that you gave it. In other words, if you want to make topological claims, training your network on data produced by LAMMPS is not the way to go. So there's a few takeaways here. In some sense, the most important one is that neural networks can classify links really well when you train them on the Writhe density matrices. So if you're a physicist, you're happy, you have polymers or links or whatnot you want to classify quickly. And so this neural network will be able to succeed in doing so. So that is a takeaway. The accuracy of these networks is independent of things like the temperature and the length of the component. It stands up really quite well. If you're a mathematician, however, you're not so happy because this study has failed to demonstrate that the Writhe density matrix includes any kind of topological invariance. And in fact, it seems rather quite compelling that there are other things going on. In fact, some people published a paper recently where they showed that if you train your neural networks, everyone has been using LAMMPS for a while, but if you produce your data using something other than LAMMPS, suddenly the Writhe density matrix trained networks fall down, massively. And so, Writhe density matrix is a useful tool, but it is not at the moment going to be used by mathematicians.